It's Paul Bamberg welcoming you to R Script1D for Math23c. Every week the D script, D for data, will show how R can be used to analyze real-world data sets. Since the subject of the week mathematically is logic, what we're going to do is build and use a data frame that has a lot of logical columns. The hard part of this comes at the beginning. Every year there's a general social survey that is carried out and published on the internet. The one I'm using goes back to 2002. I picked this one because it came along with the excellent textbook by Chihara and Hesterberg that I use in Math E156, so it's one that I'm familiar with, but I looked on the internet and I think I found them up through 2014. If you like these, you might want to use them someday for a term project. So let's see what we've got. This is a gigantic CSV, comma-separated variable style file. You don't want to display the whole thing, but the R function head will display the first 6 rows of any data frame. So let's look at what we've got. We've got 6 rows that tell us more than we ever wanted to know about the respondents, what region of the country they lived in, gender, race, education, marital status, religion, whether they're happy, how much they earn, political party, and so on. And I'm going to cut this down substantially for illustrative purposes by building a subset of the rows in this data file that have the following property. First, the gender is not marked as not available. That's what is.na specifies. Second, is.na marital is false. They're willing to tell us whether they're married or not. They're willing to tell us the religion. They're willing to tell us the political party. They're willing to tell us whether they own a gun. And furthermore, their response to the "do you own a gun" question was not "I refuse to answer." They tell us, or they make available, who they voted for in the Bush versus Gore election in 2000. And furthermore, they either voted for Bush or they voted for Gore. I'd forgotten briefly about Ralph Nader, but this will eliminate the rows corresponding to people that vote for Nader. Which is a wonderful operation in R. What it does is it looks at a vector and selects from that vector the indices of all the rows for which the value is true. So all the rows that meet our criterion will be in index. Let's try it. Well, the length of index was 555, so we still got 555 rows to deal with, and I am going to save all 555 rows in a data frame that I'll call GSS cleaned. If this were a data science course, which it's really not, we'd probably spend a lot of effort on cleaning up data sets. Since it's a math course, I'm going to provide you with a bunch of fairly clean data sets. But when you go to do your term project, you're going to have to do some cleaning on your own. And I'm going to try to set up a system throughout the course to encourage people to go online, find interesting data sets, or conduct experiments and create interesting data sets, and then post them as CSV files for the class to work with. Okay, I'd like to get just 6 of the many columns out of this database, so I will store the gender column, the marital column, the religion column, the political party column, the do you own a gun column, and who did you vote for president column. And notice I specified index as a subscript for these. Index is a vector. This automatically extracted all 555 rows. So we now have 6 vectors, each with 555 components. And now I'm going to turn them all into true-false, exploiting the fact that the is equal operator, represented by a double equal sign, is vectorized. So if you apply it to 2 vectors, it puts a true in any position where the 2 vectors are equal, and a false in any position where the 2 vectors are unequal. So I will construct gender2 equals the string male. That will give me a true in every position where the individual responded, my gender is male. I almost never do anything in R without checking that it worked. One of the reasons I think you'll find this friendly to work with, even if you've never programmed in any language before, is you run it a line at a time and you test every line as you use it, so that if you make a mistake, you know instantly where things have gone wrong. Let's just look at the head of the gender2 column. We've got 3 males and 3 females, and then look at the head of the vector we just created called male. That has true in the male positions, false in the female positions. It's working, and the same thing is going to produce true for married and true for Protestant. The political party turned out to be substantially trickier to extract, as I discovered when I printed out the vector for political party, because it turns out there are 3 flavors of Republicans. There are ind near rep, which presumably means independent but more nearly Republican. Then there's not strong Republican and strong Republican. So what I had to do was to start using logical operators. I said, take the truth value, political party equals strong rep, or it with the truth value of ind comma near rep, or that with not strong rep, and store the result in a vector named Republican. Never do anything without testing it. I look at the first 6 entries in the political party, and I see that the first 5 are various flavors of Republican, and the 6th one is other party. And when I look at the resulting logical vector, I see to my delight it's got 5 trues followed by a false. Finally, I'll make a column which is true when the individual being surveyed voted for Bush. And now I'll combine these into a data frame, which I will name GSS Logical. And when you look at this, wow, it looks kind of like those truth tables we were doing in the previous script. It's got a lot of columns, each consisting just of the values true and false. And now we can apply all sorts of logical operators to those columns, thereby applying our newfound knowledge of logic to data analysis. Let's save this. I might want to write a homework problem based on it. And as I said before, you can always inspect these CSV files in Microsoft Excel or other database program or spreadsheet program, or you can just look at it as a text file. Now let's start looking for individuals that meet certain criteria. Let's figure out which of our 555 people own guns, for example. So what I do is say which, and then provide the logical vector gun owner in this data frame, And what I will get back is a shorter vector which will contain the indices for all the rows, all the individuals who own guns. Individuals 2, 3, 4, 9, 11, 14, and so on own guns. And since the length of the vector guns is 209, we know we've got 209 gun owners in our database. Now we can start doing some sociological research. By using the logical AND operator, we can extract the gun owners who voted for George Bush in 2000, and we'll store that in guns Bush. When I look at that, well, the first 6 are the same, and in fact, there's still 141 entries in this vector, so we know that of our 209 gun owners, 141 of them voted for George Bush rather than Al Gore. If we use and not, so we look for rows that have true for owns a gun but did not vote for Bush, we get all the gun owners that voted for Al Gore, all 68 of them. A nice way to consolidate these data is into what data analysts call a contingency table. And in order to do that, I just specify the names of the 2 columns. I say, oh, I want a table made from the gun owner column and the voted for Bush column. And when I display that, the only tricky thing is remembering whether it's rows or columns that correspond to gun owners. The rule, it turns out, is that the first argument corresponds to the column labels, the second with the row labels. Did I get that right? Well, let's check it. Because I can do the same thing with my cleaned table, and that has no yes for gun owners as the row labels, and Bush Gore, the second argument, as the column labels, which means I messed this up. And since I don't want to re-record the whole thing, I'm just going to correct the error. Now, if you think about this table, you realize there's only one independent piece of information in it, because we know how many people own guns, how many don't own guns, we know how many voted for Bush, we know how many voted for Gore. If we know how many gun owners voted for Bush, we know everything else. An interesting thing to do is to compare this table with what we would have got if gun owners were equally likely to vote for Bush or for Gore. What we'd expect if voting for Bush and owning a gun were independent factors. And R has a very useful function for calculating this. It's called outer. What it does is it takes 2 vectors and applies an operation to each pair of entries. The default operation is multiplication, so I didn't even have to specify it. But if I had put comma plus, it would have added them together. So this takes all possible products of the row sums and the column sums, and then it divides by the sum of the entries in the table. Since it was multiplying first and then dividing, the net effect of this is that the sum of all the entries is going to be the same as the sum in our original table. So let's compare these. This is the actual contingency table. This is the contingency table that we would have got with the same number of gun owners, the same number of Bush voters, if whether the gun owner voted for Bush or for Gore had been settled by a chance device that work the same for gun owners as for non-gun owners. Or if you want to put it in probabilistic terms, if voting for Bush and owning a gun were independent, we've got a table that looked like this. This is the table we actually got. And you look at this and you say, this is kind of interesting. We had true in the gun owners column 97 times expected. But if we look at the people that didn't vote for Bush, we discover there were actually only 68 rather than the 97 we expected. If we look at true, on the other hand, we would have expected only 111 gun owners who voted for Bush, whereas we got 141. Is this significant or not? Well, over the next couple of weeks, I'll teach you principled ways to answer this question, but I'll take the elementary statistics course approach. You throw the result into some test and trust that it's doing the right thing. And in R, this is called the chi-squared test, chi-sq.test. I throw the two vectors in, and it gives me back something called a p-value. This p-value is 3 times 10 to the minus 7th. And what that means is that, according to this test, the probability that this large discrepancy between observed and expected values would have arisen by chance is roughly 3 parts in 10 to the 7th. Pretty small, and therefore it's probably reasonable to conclude that gun owners were inclined to vote for Bush in 2000. Next week I will show you much more compelling ways of calculating this number so you actually believe it. For this week, I'm just going to show you how to run the test. And now we can have some fun with this table. Is being Republican likely to make you vote for Bush? I'd expect the answer to be yes. And when I look at the table and the expected values, you see that it is wildly true. Republicans tended to vote for Bush. Non-Republicans tended not to vote for Bush. And if I asked the chi-squared about this one, it said the probability of getting this large a discrepancy by chance is about 1 part in 10 to the 16th. Let's see if we can find something where we don't get such a tiny p-value. It seems reasonable that religion might well be independent of gender. We can answer this question by making a table out of the Protestant column and the male column. I look at the table, I look at the expected values, and now you see the discrepancy is quite small. Getting a pair of falses, not Protestant and female, we had 109 rows, and what we would have expected was 118 rows. That discrepancy of 9 could well have arisen by chance, and if I apply the chi-squared test to this pair of vectors, the p-value is 0.14, which means 14% of the time you will get this large a discrepancy just as a result of chance. So drawing the conclusion that the females were strongly inclined to be Protestant would probably not be well justified. Okay, that was a data frame that had nothing but logical columns in. Let me show you how to work with one that has some numeric columns. Here are some data about the Red Sox in 2013. All of these are on the course website, and I'm expecting that you will download them into the data subdirectory of your Math23c folder, which is where they get looked for. And if you look at this, you discover you've got game-by-game data. Whom were the Sox playing? Did they win or lose? How many runs did they score? How many did the opponent score? Was it a day game or a night game? What was the attendance? What was the duration? Presto, you're an instant baseball researcher. And since R functions tend to act on vectors, you can get lots of answers without doing anything that remotely resembles programming. What was the mean attendance at these games? You call the function mean. It looks at the vector of attendances, averages them all up, and says the average attendance was 34,571. What was the median attendance? No, sorry, not the median attendance, the median duration of a game in minutes. This is one of the reasons I've got a bit tired of baseball. 195 minutes, 3 hours and 15 minutes. What was the mean? A little bit longer. Maybe the reason it was a little bit longer was because of extra inning games, which can go very long. How long was the longest game? We call the function max. Wow, that longest game ran 6.5 hours. What was the shortest one? Shorter than 2 hours, probably because rain started to fall. Now let's start exploiting the fact that if we use the value true in an expression that's looking for a numeric value, it converts true to 1. So think about Sox 1 lost is equal to W. That's true if the Sox won the game. If I apply mean, which wants to look at numbers, it's 1 if the Sox won the game. So this is taking the mean of a vector which has a 1 in the position of games that the Red Sox won, a 0 in positions where they lost. What are we calculating? We're calculating the percentage of the games that they won. This year they won 60.6% of their games. What proportion of the night games did they win? Well, I can answer that question easily enough. I take an expression that's 1 if the Sox won the game, multiply it by an expression that has the value 1 if it was a night game, divide the sum of all those products by the number of night games, and presto, I see that the Red Sox won only 58.6% of their night games. And maybe you're already starting to think like a statistician and asking yourself, does that indicate the Sox fared better in the daytime, or was this discrepancy small enough that it could just have arisen by chance? Next week, I will show you how to run a so-called permutation test to answer that sort of question. Now let's look at how R will let us display this information. I look at day-night and I call the function table, and it says the two values in this column are D and N, and here's how many times they showed up. It's a little bit prettier to ask for a bar plot of this table, and this shows bars whose heights are proportional to the number of day games and the number of night games. Notice when you're using bar plot to display the contents of a vector, first you convert it to a table, then you call bar plot on that table. Let's try the same thing with the number of runs the Sox scored. And you will notice if you look at this, there were no games in which the Sox scored 14, 16, 18, or 19 runs. When I do a bar plot, those values for which 0 counts occurred are not displayed at all. This is a feature of the bar plot that is sometimes unappealing, and if you don't like having the 0 values left out, you can do an alternative. You can make a histogram. If you call hist on a vector, you don't have to make it into a table, then you get a histogram of the numerical values. R tries to bin these together in a way that it thinks is sensible. I think the values over the 5 here are probably 4 and 5. These may be 9 and 10. But if you don't like the way the histogram is putting them into bins, there are ways of specifying the breaks in the histogram, and here I said I'd like breaks on all the integers between 0 and 25, and now I have 0 runs, 1 run, and so on, and you'll notice that we have a blank column in the histogram for 14, 16, 18, and 19 runs scored. If you have a very large number of distinct values, as is the case for duration in minutes of the game, then the table gets rather long and the bar plot becomes rather unenlightening. We do have a bar in that plot for every duration that actually occurred during the season, but in this case I think the histogram is vastly superior. The default uses a bin size which is too large for my taste. I have found in general, if you say breaks equals the string capital F, capital D, these are the first letters of a couple of statisticians that invented the algorithm for putting this break in, you tend to get somewhat more columns, and I find that a bit more to my taste. If I want to be really in control here, however, I can say I want a sequence of breaks that starts at 90, goes up to 360 in increments of 5, and because I started at 90 and went by 5s, it's going to put in labels at 100 and 350, and that's quite a satisfactory histogram of the results. I can do the same thing with attendance, and I'm quite happy with the result produced by the FD breaks. Now, you've already seen that the is equals operator is vectorized. So are the greater than or equal to, and less than operators. So we can use these to make logical columns out of numerical ones. Socks won lost is equal to W. That's going to produce a true in every position where the Sox won the game. I check it, and you can see I started with 1, 1, lost, 1, lost, 1, and that got converted to true, true, false, true, false, true, trues in the positions where we had a W. More interesting, Sox $R, number of runs scored by the Sox, is greater than 4. That's going to produce a true for all games where the Sox scored more than 4 runs. And sure enough, that's the case. Where they scored 8, 7, 6, or 13 runs, we got a true, and the other 2 cases we got a false. Here's one for day game. Here's one for big crowd. Big crowd is attendance greater than or equal to 40,000. Quick game, baseball being what it is these days, is a duration of less than 3 hours. Home game is not. Sox away is true. And now I can make myself an all-logical data frame out of these Red Sox data with 6 columns corresponding to did they win the game? Did they score more than 4 runs? Did they give up 3 or fewer runs? Was it a day game? Was it a large crowd? Did it get over quickly? Was it a home game? And whoops. I just neglected to run that line. So now out of this data set that contained a lot of numerical values, I've produced something that's all logical. If you're starting to get keen on applying data analysis to your own subjects of interest, you might want to try this out for yourself. You'll certainly end up doing something like this later on for the term project. Let's save this. I might want to turn it into a homework problem, though I don't think I've done so yet. And now let's use our logical operations to do some data searching. Let's look for away games where the Sox lost the game even though they scored more than 4 runs. We do this using which. We take something that will equal true if our conditions are satisfied, that is, scored more than 4 is true, and home game is false, and 1 is false. And we discover there are only 6 games that meet the criteria. Let's have a look at one of these rows. The first of these rows is row 26. If I want to look at the first column in row 26, I say Sox logical 26, 1. So you can treat this database, this data frame, the way you might already be accustomed to treating a matrix. Row index first, column index second, and it says the first entry in row 26 is false. If I want to look at the whole row, I just leave the second index blank, and now it gives me the whole row and obligingly provides the column headers on top of them. Another way of getting the first entry in this is to use the $sign syntax that selects a column from a data frame and say row 26 $1. So you can either use $1 numerically to select the first entry, or you can use the name of the column to select it. Now we can start exploiting the fact that true is 1 and false is 0. How many home games? We just take Sox logical home game and sum up all the ones we get for the trues, and we discover there were 89 home games. Some of them, by the way, were postseason games, in case you're thinking that's not half of 162. What percentage of their games did the Sox win? I just take the mean of the logical values in the 1 column, and we've seen this before. They won slightly more than 60% of their games. What about away games with big crowds? Well, we want home game to be false, we want big crowd to be true, and we sum up the number of times that happened. They won 31 away games with big crowds. I did that first with the ampersand operator, combining true and true into 1, and then converting that to a single 1. So this is true, and true equals true, and the resulting true is treated as a 1. Alternatively, I can convert these both to either 1s or 0s and multiply them together. I get exactly the same result, and I had to do a bit of experimentation to realize that I needed parentheses around the first factor to get this to work. What fraction of the games did the Sox win when they scored more than 4 runs? Easy. I just multiply the logic value in the 1 column by the logical value in the score more than 4 column, divide by the sum of the score more than 4 column, and I've got the answer to my question. So that will give you the flavor of how one can start to do data analysis in R. In my opinion, the nice thing about this, especially if you're a beginner, is you can do it one line at a time, and you never have to write the sort of for loops that dominate elementary programming courses, because you can do almost everything by exploiting the vectorized operations in R. Well, this has been a rather long script. Let's see if I can successfully upload it to YouTube.